Meat tenderness is one of the crucial quality characteristics that have a huge impact on the customer satisfaction and customer purchasing decisions of choices. In the meat industry, one of the challenging parts is to retain the nutritional and sensory qualities while enhancing the tenderness of the meat. So, what is the common method for tenderizing meat? One of the common techniques for tenderizing the meat is mechanically induced tenderization by using a meat mallet. It involves using a meat mallet to physically break down the tough muscle fibers and connective tissues in meat. By pounding the meat with the mallet's textured surface, small tears will be created. Next is enzymatic tenderization, which utilizes natural enzymes to hydrolyze muscle proteins. Papain is a natural enzyme extracted from papaya that is used to tenderize meat. It works by breaking down the proteins in the meat, making it softer and tender. This lab demo aims to compare the effects of mechanical tenderization using a meat mallet and enzymatic tenderization using papain from papaya on the quality attributes of meat. Specifically, the water holding capacity, shear force, and cooking loss of treated and untreated meat samples. The first objective is to compare the effect of different treatments, which is better, mechanical tenderizing using a meat mallet or enzymatic tenderizing using papain enzyme from papaya on the water holding capacity of the cooked meat. The second objective is to determine the effect of different treatments on the shear force and the cooking loss of the cooked meat. First of all, any excess fat of each selected cut of meat was carefully trimmed and inspected to confirm it was ready to proceed. Then, each of the meat was weighed separately and their initial weight was recorded. For the controlled meat sample, the meat was placed in a pan that has been prepared to a medium temperature. About 3 minutes was spent cooking the meat on each side. For the mechanical tenderization technique, a metal mallet with a textured surface was gently pounded on the meat while ensuring a uniform coverage. After that, the meat was placed in a slow-heated pan and was cooked for approximately 3 minutes on each side. Next, for the enzyme tenderization technique, the papaya was carefully sliced into small pieces. Then, the papaya pieces were blended into a smooth, consistent paste using an electric blender. The freshly prepared papaya paste was evenly spread across the surface of the meat. This ensured thorough coverage, allowing the enzymes in the papaya to work on tenderizing the meat fibers. The coated meat was placed into the chiller, where it was left to rest for 30 minutes. During this time, the natural enzymes began breaking down the tough muscle fibers tenderizing the meat. After refrigeration, the meat was put in a bowl and rinsed thoroughly under cold running water. This step helped remove any remaining papaya residue, ensuring that the meat was ready for cooking. Then the meat was then cooked for approximately 3 minutes on each side. Afterwards, all of the meat samples was let cool on the cutting board before their weight after cooking was recorded. Now let's determine the water holding capacity, cooking loss and shear force for each sample. The water holding capacity is analyzed by using the press method. 3 grams of meat is weighed using the analytical balanced. Then the meat sample was placed between 2 pieces of Whatman No. 1 filter papers. The filter papers with meat samples was placed on the flat surface and covered with a piece of plastic. The samples was pressed using 2 kg of load for 2 minutes. The weight of the pressed sample was weighed and the WHC was calculated using this formula. And for the cooking loss, the weight before and after cooking was recorded and calculated using this formula. To determine the shear force, the cooked sample was cut into 1 cm width, times 1 cm thick, times 3 cm length, parallel to the microfiber. The sample was sheared perpendicular to muscle fiber orientation and the peak of shear force was recorded in kilogram. According to the result, meat treated with the pounding method has the highest water holding capacity value, which is 95.32%, followed by enzyme, papain, and control sample with 93.24% and 92.44% respectively. Pounding meat using a meat mallet is one of the methods for mechanical tenderization, where it disrupts the muscle fibers which breaks the meat's external surface and releases the myofibrillar protein. So, the increase of available protein in the structure enhances the water holding capacity by increasing the surface area for water binding. Based on Ham and Nerol, 1977, marinating meat in papain hydrolyzed muscle proteins, then breaks down the actomyosin complexes, leading to high water retention. Thus, it explains the high value of water holding capacity of meat treated with enzymes. For cooking loss, the control sample has the highest cooking loss with 45.6%, followed by pounding, and lastly, meat treated with papain. This is because both treated meat has higher water holding capacity values, resulting in a higher cooking loss value for the control sample. The pounding method, using meat mallet, increases the cooking loss due to the damage of the fibers, which affect the meat structure's integrity, leading to high amounts of moisture loss. Although this treatment increases the water holding capacity, the excessive mechanical disruption can cause cooking loss. Treating meat with enzymes like papain can tenderize meat without significantly increasing the cooking loss value, as it breaks down specific protein like insoluble connective tissue, which does not alter the structural protein that is responsible for water retention. This proves the least amount of cooking loss values in enzyme-treated meat. Move to the shear force test. The results show that the control sample has the highest value for both firmness and toughness, followed by enzyme papain-treated and pounding methods. This indicates the pounding method affects the tenderization of meat the most, rather than enzyme papain-treated and control sample. According to Azmi et al., 2023, pounding meat reduces the firmness and stiffness of meat by breaking down its structural components. Pounding meat tenderizes it by separating muscle fibers and connective tissues, reducing stiffness and roughness, thus alters the structure of collagen, making the meat softer and easier to chew. To sum up, this lab demo demonstrated that both the pounding method and enzymatic treatment with papain are effective in enhancing meat quality by improving water holding capacity, reducing cooking loss, and increasing tenderness. The pounding method, a mechanical tenderization technique, increases water holding capacity by disrupting muscle fibers and releasing proteins that bind water. However, it also causes structural damage that can result in higher cooking loss. In contrast, papain treatment enhances water retention by hydrolyzing muscle proteins and breaking down actomyosin complexes while minimizing cooking loss due to selective breakdown of connective tissues without compromising structural proteins. Both methods significantly reduce shear force, with pounding being more effective at breaking down muscle fibers and connective tissues, and papain hydrolyzing collagen and elastin to achieve similar tenderness. While both methods are valuable, careful control is required to avoid over-tenderizing the meat and affecting its texture. Thank you for listening.